Hi everyone on the live stream. I am here today to introduce Yvonne Pendleton, who is the Director of Solar System Exploration Research at NASA, and she began her career at NASA in 1979, has a bachelor's degree in aerospace engineering from Georgia Tech, a master's from Stanford, and a PhD in astrophysics from UC Santa Cruz. She's also a fellow at the Cal Academy of Sciences and has an asteroid named after her. So please join me in welcoming Yvonne Pendleton. Sorry, you don't need that.
It's my pleasure to bring you news from your next door neighbor at NASA Ames Research Center about what we're doing in the virtual world. So the exact title of our institute, which we call SSERVI for short, is, as you just heard, Solar System Exploration Research Virtual Institute. And it's that last part, Virtual Institute, that really makes us different from a number of other activities and things that you might hear about. So I'm going to go on in a second, but I want to first introduce to you two of our staff members that I brought with me today. We have a small central office located at NASA Ames that helps coordinate the activities of the hundreds of researchers that we have distributed across the country. And with me today, I have our staff scientist, Brad Bailey, who's here in the audience, and also Brian Day, who's our Director of Communications and Public Engagement. So when it comes time for questions, if you have any questions that pertain to either the activities of our teams or the outreach that we do, they will be able to help me answer and go deeper. Okay. So let me just start by asking, what is a virtual institute? For some of you, you may not have heard of this term before, or for those of you who have, you may have a different idea from what it is that we actually do at SSERVI. So in our idea, a virtual institute is a distributed organization that allows you to pick the very best investigations, teams, and facilities from wherever they are. You don't have to be restricted by geographical location for somebody who has a certain type of laboratory working with another group that might have more expertise, in some other area. And by sharing these students and the facilities and the resources that the various teams bring to the organization, you can actually build a stronger institute, I maintain, than if you just had a traditional bricks and mortar building. So I think you get more bang for your buck. The small office that we have at NASA Ames Research Center is able to coordinate and help the collaboration both within the teams and across the team lines. And we're able to do this across a very interdisciplinary subject area. And I'll tell you more about our subject area in just a minute. But first I want to tell you that there is a history of virtual institutes at Ames. NASA has started the NASA Astrobiology Institute, which began in 1998. At Ames, it's still going very strong. And then in 2008, the NASA Lunar Science Institute was born. That is actually the predecessor for SSERVI, and we have taken our studies of the moon and expanded them now to include studies also of near-Earth asteroids and the moons of Mars. Then we also have the NASA Aeronautics Research Institute, which began in 2012, and SSERVI was just born last year, in 2013, a little over a year ago now. Okay, so this diagram, this drawing is indicating the orbits of most of the near-Earth asteroids. I say most because we think we have found most of the large ones, but there are probably still a few that we don't know about. And when you see that kind of involvement of where they are located relative to the Earth, I think it becomes obvious why NASA felt the need to expand our purview to go beyond studies of the moon. And that's why we now include, as it says here, the near-Earth asteroids, and also the moons of Mars, which we believe may have been captured asteroids themselves. This institute is funded jointly by both the Science Mission Directorate at NASA headquarters in Washington, D.C., but also the Human Exploration side of what NASA does. And so this is a very important bridge to join together science and exploration so that you are addressing the science questions you need to know before you go. So before we take humans anywhere beyond low Earth orbit again, there are certain questions we want to address, and our teams are looking at what those conditions might be that will help us get there and get there safely. So in more detail, what does SSERVI actually study? Well, we have a long list of items here, but the role of the moon is still very important to what we do. We study the origin, the composition, the dynamics of all of these bodies. So we'd like to know in particular what kind of questions cover multiple bodies. In other words, if you were interested in the dust or the regolith that sits on the moon's surface, you might have some of the very same questions that apply to the moons of Mars, Phobos and Deimos, and similarly to asteroids. And by understanding the composition of these materials, you would better be able to design both vehicles and environments for humans to live in on any of those bodies, or even just to go there for a short time to work. Volatiles, in its broadest sense, these are materials that may be able to be liberated up from the surface, or ice from down deep inside of a crater. Those are very important to us as well, and they cover, again, the multitude of the bodies that we study. And you can read down this list a number of the other areas that SSERVI is concerned with. So we put out a proposal a little over a year ago for teams to reply to, and from that we selected 9 teams. And here are the principal investigators that make up the current composition of the SSERVI Institute teams. And you can see that the principal investigators, just in alphabetical order here, I've got Bill Botke, who is from the Southwest Research Institute, and Dan Britt, who is from the University of Central Florida. Ben Bussey from the Applied Physics Laboratory has just recently been replaced by Andy Rivkin, because Ben Bussey is now the chief scientist in the Human Exploration and Mission Operations Directorate at NASA headquarters. Then we go on to Bill Farrell, who is at the Goddard Space Flight Center. This is on the East Coast, just outside of Washington, D.C. Tim Glotch, who is at Stony Brook University up in New York. Jennifer Heldman from NASA Ames Research Center. Mihai Harani at the University of Colorado. David Kring, who is in Houston at the Lunar and Planetary Institute. And Carly Peters at Brown University. So each one of these principal investigators put together the very best team they could find. They're usually somewhere around 30 to 50 people in number, and they could be located at the university or facility that I just mentioned where the principal investigator is, or maybe not. They themselves would have a distribution across the country. And all of our teams communicate using the virtual technology that I'll tell you a little bit about in a minute. And we get together once in a while in person, but by and large, these are virtual communications. Okay, we also have 8 international partners. Why would international partners care about joining a domestic group like NASA's SSERVI? Well, it turns out through a no exchange of funds basis, if they become a partner with us, it facilitates their getting the resources within their own country to develop whatever kind of program they wanted to develop that's relevant to what we do. Perhaps it's investigating the moon, or in the case of Korea, they're very interested in going to the moon with a mission themselves. Whatever the country's interest is, if it relates to what we do with our domestic teams, we are happy to entertain a proposal from them, and so far 8 of them have been accepted into our international family. And then we urge cross-collaboration between the domestic teams and the international partners, and that's going really well. This is a distribution of where the principal investigators and the co-investigators are just for the domestic teams. And again, just to give you an idea that there a total of 318 researchers, including the students. There are many students that are involved with these teams, and the average team size is roughly 30. We have one that's up to 60 in number. Okay, so getting down to more details about what these teams actually do, I've selected just a few research highlights. They have many. I mean, each one of these teams could easily take up an entire hour just to tell you the fascinating work they're doing. But let me just give you a few highlights. So Dan Britt at the University of Central Florida has a team called the Center for Lunar and Asteroid Surface Science. And they study the physical properties of regolith, the dust that we talked about on the surface of bodies like the moon, but also asteroids and the moons of Mars. The geotechnical properties, the microgravity effects that you might encounter, impact ejecta, dynamics, hydration and weathering of the near-Earth asteroids. Over time, the 4.5 billion years that these bodies have been in space, there's been a lot of weathering that's happened. And the charging and mobilization of dust on the surface of any of these is going to affect any machinery you're going to put there, and certainly the astronauts themselves. So then the next one, Andy Rifkin, the Applied Physics Laboratory at Johns Hopkins University. Their team is called Vortices, a very long name, and NASA loves its acronyms, so you can see how they developed vortices out of their name. But they study volatiles, regolith, and thermal investigations. They look at the sources, sinks, and processes, and the interaction that various materials will have with the regolith, and the evolution of that dust on all of the target bodies. Okay, the group at the Goddard Space Flight Center, led by Bill Farrell, this is called the Dream 2 team. And the reason it's called Dream 2 is because Dream 1 was part of the NASA Lunar Science Institute, which I was also the director of in the last couple of years before it transitioned into SSERVI. So I got to know the teams from the NASA Lunar Science Institute pretty well, and I was really pleased that when we had our peer review process of the proposals, it turned out several of the principal investigators who had been leading teams under the Lunar Science Institute were selected for SSERVI. So Bill Farrell was one of those, and the dynamic response of environments at asteroids, the moon, and the moons of Mars is what he calls Dream 2. They study plasmas, the plasma interaction that comes from the solar wind. When the solar wind comes and interacts with a body like the moon, it does a number of interesting things. And the fact that we now see OH all over the surface of the moon, and the solar wind contains hydrogen as it's traveling and runs into the regolith on the moon, you can see how the H and the OH can get together and form water. So the plasma processes as they interact with the moon and the other bodies are very important. And you can also see here that we have the solar wind charging of asteroids. This is something else that they study. They model this. We have a lot of interesting results that show the kind of things that you need to think about when you're looking at the charging from these kinds of interactions. Timothy Gloch from Stony Brook University has a team that they call the RISE team. And they do the remote sensing of airless bodies, field operations, and metrics for human exploration. They look at the reactivity and the toxicity of regoliths. These can be dangerous to humans. So, when the astronauts were on the moon, the spacesuits were just covered with dust. And getting back into the vehicle, this is a concern, because if you're breathing in that dust, it turned out it was a very sharp, jagged kind of material, and it can be really, really harmful over a long period of time. So they look at that and try and understand what we have to mitigate against. They also do synchrotron analyses of samples, and they look at volcanics and impact crater analog research, which means you go to places on the Earth that look like good analogs for the places you want to go in space, and you try out some of your machinery and some of your techniques to see how they would best work. Okay, continuing on, Mihai Hirani from the University of Colorado, his institute team called IMPACT has developed the world's fastest dust accelerator, and this is open to the entire scientific community and exploration community so that people can take samples there, they can try out new experiments, and it's really going well. They're doing a lot of phenomenal work. And they have just built a new ion gun that simulates the solar wind so that they can extend this research even further. And here you can see the penetration and the charging studies that they do as well. Carly Peters from Brown University, her team does a lot of interesting stuff with the evolution and environment of whatever destination we're going to go to. But I'd like to really highlight the work that they've done on the moon, because I think one of the most exciting results that we've learned about the moon is the fact that it's so wet. Now, it's wet compared to what we thought it was. It was so dry. A few years ago, we thought we thought it was very dry. And it's maybe about as wet as the Sahara Desert, but that's still a lot wetter than what we thought. So to put it all in perspective. But the water is in very different locations, and that indicates it came from probably at least three different sources. And the one that we found inside the crater when we had the L-Cross mission, I'm sure many of you would remember that a few years ago in 2009. This was a mission that went to the moon, deliberately crashed into a crater, kicked up, excavated a bunch of material, and then studied what the composition was. The L-Cross mission, which was developed at Ames, revealed that we had water ice in the bottom of a crater, the Cabeus crater. Well, that was great confirmation. We were all very excited about it. But frankly, I wasn't all that surprised. I kind of thought there would be ice down in the bottom of a crater. What I didn't expect was that we have water in the rocks that came up from deep inside the moon that the astronauts picked up. In the Apollo samples, it turns out some of those samples that they brought back contained glass beads, volcanic glass beads, that could protect the water inside it. And now, all these years later, we have the technology, we have the instruments to go back and analyze those samples in greater depth and differently. And that's where we found quite a bit more water than we previously thought. And then the third component of water I already mentioned to you, which is the OH that exist literally across the moon in very different terrains. And the interesting thing about that is that it seems to be replenished on a current cycle. This isn't just water that was deposited a long time ago, like deep in the crater, that happened a long time ago, and that's that, and this is now. We think we're seeing actual replenishment in these different scenarios, not the water deep in the moon coming up, but of the one on the surface and also some of the craters. And that's fascinating to me, because that just changes a lot of the physics of what we thought was happening on the moon. And if we understand how it's happening on the moon, we then understand more about how it could happen on Phobos and Deimos and other bodies, other near-Earth asteroids that we might go to. Okay, so going on to a couple more of our teams. Bill Botke, who runs a very interesting team out of the Southwest Research Institute in Boulder, Colorado, they do a lot of theoretical modeling where they look at the dynamics and the formation of the early solar system. In fact, in just about a week, I'm going to be at a conference. It's all about early bombardment of the solar system. And they'll be talking about what happened when, what big bodies hit the Earth and the Moon, what they did, when they hit, how they affected the other terrestrial planets. And computer models can really tell us a lot about how all of this happened. The migration of planets from the early part of the solar system to today has a lot to do with the dynamics that these bodies found themselves on, the trajectories and that sort of thing. He also looks at things like how asteroids could be stuck together or how easily you could pull them apart. One of the concerns we have with asteroids is that some of them seem to be extremely fragile, And you don't want to have a mission to an asteroid that you go up to, and as soon as you touch it, the whole thing falls apart. Now you've got a whole bunch of little, or maybe not so little pieces. And the models that we have are helping us understand how that works. Jennifer Heldman at Ames Research Center is leading a team that she calls FINESSE, a very nice acronym. And what she's doing is looking again into the Earth analogs that I mentioned just a little while ago, so that you can really understand what you should do when, if you were out exploring, both with humans and with machines. So for instance, their team went to a couple of places in this past year, and the one that I'd like to tell you about is in Idaho. It's called Craters of the Moon. Maybe some of you have been to this national monument. And they looked at the way you would operate machinery from a distance, you know, simulating what it would be like if you had a back science room here on Earth trying to run something on the moon or on an asteroid. And so they did quite a bit, building in the time delay that you'd have in communications, things like that. Let's see. And the last team that I want to mention here, David Kring from the Lunar and Planetary Institute in Houston, they study the inner solar system impact processes. And you'll see a similarity in themes and all the things I'm saying here. It's probably kind of blending together, like which one does what. Well, you know what? That's exactly the purpose. We want them to blend together. We want to not see the lines between what these different teams do, because I believe it's by the collaboration and the crossover of what these teams bring to the table that new science gets developed, new directions are found, and this is where the most creative discoveries seem to be happening. So what David does is he looks at the impact history and processes, the geochemistry of the regoliths, and age dating of regolith materials. He looks at the near-Earth asteroid identification and characterization, and he also works a lot with the next generation training of both the young people that will go into these fields and also astronauts, the new classes of astronauts, so that they know how to identify rocks and, you know, the geology side of what astronauts need to know, as well as a few other things. And some of the things that his team has just recently finished, they did a global lunar landing site database that is now open and available for the entire community. So these teams are creating materials that are available not just for the teams themselves, but to the entire science and exploration community. Okay, so another thing that we do within the Virtual Institute that I really like a lot is we build and share facilities. And this first picture that we have here is about the dust accelerator that I mentioned at the University of Colorado. And that was up and running actually during the Lunar Science Institute, but again, because Mihai Hirani was one of the principal investigators who led a team under the Lunar Science Institute that is now part of SSERVI. And at Brown University, there's something called ReLab. This is a spectroscopy lab where they look at samples and help people analyze and understand what their field samples are made of, and the new components that they make as well. And at Brown University, they've also developed something that is a 3D immersive environment, which is something that I think the Google folks would be especially interested in, so that you feel like you're there and you look around in all directions and it's just like you're really there. And this was modeled after the what we call the Keck Caves, which are at UC Davis. Maybe some of you are familiar with that, but they have the same kind of facility now at Brown University. Okay. Wait a minute. Okay. And at Ames, we have a couple of facilities that we share as well. There's a regolith test bed where we have 8 tons of simulant of lunar material, and we have little rovers that run around in this yard. I use it with students remotely. They can be across the world, and they can operate the rover, and we've built in little lessons where they can go up and try and identify the difference between a meteorite and a rock and take pictures of it, that sort of thing. There are scientific uses for the test bed as well. And at Stony Brook University, there is a vibrational spectroscopy lab. And this is, again, something where people would bring their samples to it and try and understand, or something that they've built or created, and try to understand more about how it would interact with or be interacted on by some sort of process, and also what it's made out of. Okay, another part I wanted to stress is the SSERVI team collaborations that we have across the team lines. And so just a couple of examples. This first one came about in the very first experience where we brought the principal investigators together to meet for the first time. And over this 2-day period where they met face-to-face, we were at NASA Ames, we asked them to please come up with a list of areas where they thought their area could cross over and they could find a collaboration with one of the other teams. We had each of the teams give a little synopsis of what their proposal was. Now keep in mind, these were teams that were competitors just moments ago, and now we're asking them to share everything. Share your data, share your processes, tell us what you're going to do, and look for ways, trust each other and look for ways to work together. And they did it instantly. And one of the ideas that came out of it was to have this sample repository at the Natural History Museum, where any team that collects any kind of field sample or had a sample that they made could bring it together and put it in one place, so that if you wanted to do some sort of process on it, you could know that you were using the same rock. 2 different teams doing 2 different processes on the same sample is a lot better than using 2 entirely different samples that you just happen to think are the same rock or the same material. And this one ran into just a little bit of a hiccup, because it turns out the Natural History Museum does not take samples that are found on Earth, but they only take samples that you create. So we're looking for another home for the actual field samples at this point. But this was a great idea, and they started putting all their materials together right away. And I was just really pleased to do that, to see that happen. And another one is the asteroid modeling. So the dynamics that we talked about with the early solar system and what happened to it when you had all this bombardment in the early days, when you couple that to geochemical studies of the rocks that people have found, either from meteorite samples that have come off planet, from someplace else, or the lunar samples that came back from the moon, you couple that together with the dynamics and you can learn an awful lot about what happened when. And what we call the late heavy bombardment period that affected both the Earth and the Moon system is one of those times that we'd really like to understand better, because it looks very, very likely that the Moon formed out of a giant not giant, but a Mars-sized body hitting the Earth. And when it hit the Earth, it knocked off a great deal of material, and out of that formed the Moon. But what didn't make sense for a long time were the isotopic studies that we had and the chemical composition between the Moon and the Earth. Those are now coming into much clearer focus in terms of how hot the Earth was, how wet the Earth was, how big that body was, what kind of angle that body had to hit the Earth at in order to make what we end up seeing on the Moon. So it's just amazing that dynamicists and geologists getting together are making these kind of strides forward. I mean, those people would not even have gone to the same conferences. So they wouldn't have met, they wouldn't have talked, they wouldn't have shared down to this level the kind of research they're doing. And now they are, and out of that grows new science and new discoveries. So isn't that cool? So let's see, I've already said this about facility sharing and sample analysis, so I will skip that. We also ask that the international partners collaborate with the domestic teams. And so that Crater of the Moons campaign that I mentioned that Jennifer Heldman was running, that also, and Timothy Glotch, his team was part of that as well. That also had our Canadian partner as part of it. The dust accelerator that I mentioned, that was built with our partnership with Germany. So we can see an awful lot of the international flavor coming through as we move forward with first the Lunar Science Institute and now with SSERVI. So now I'd like to mention the Resource Prospector mission for just a second. SSERVI has several people in and among our teams that are actively engaged in this. And Terry Fong, who's here in the room today from NASA Ames, is the deputy manager of the rover part of this NASA mission. This is a mission in development with the idea of developing technology that's generally applicable across many different target bodies, but ostensibly it would go to the moon. And the proposed mission demonstrates in situ resource utilization. In other words, you would collect and use the materials that you find on the body. And various critical mission aspects are being developed at NASA Ames. It has a lunar rover carrying the regolith and environment, science, and oxygen, and lunar volatile extraction payload. Oh my gosh, that's a ridiculous payload acronym name. It's called RESOLVE. Okay, and preliminary testing has been conducted on Mauna Kea in Hawaii, one of my favorite places, in conjunction with the Pisces group there. Anyway, SSERVI is facilitating the site selection and the analysis activities for this mission, and a number of our investigators are involved, and we're very excited. We hope that this mission goes forward. Okay, there are a lot of words on this page. Main point is I wanted to tell you that our central office does a whole lot more than just send out the money. Our institutes, each one of the teams are funded for 5 years, which give them long-term stability, and that's great for them. But what we also try to do is make sure that we at the central office take care of the big problems. Anything that would slow them down and take them away from their research, we would like to handle at the central office. And then beyond that, the actual running of the institute, we do an awful lot of community engagement. Our job was to bring together the scientific and the exploration community. And again, those are groups that don't often mingle, but to show them that they had a lot in common and they had things that they needed to learn from each other. And so to do that, we have a lot of various activities here.
All right, so we have a number of things that we're doing to keep ourselves busy. We have the Exploration Science Forum. You're going to be hearing more about that, but that is our annual conference that we have at NASA Ames, where we have people from around the world gathering and talking about lunar and planetary science and exploration technologies. We also help coordinate a European conference, the European Lunar Symposium, with our partners that we have in Europe. In terms of citizen science, we've been working successfully. We've been involved with the LCROSS and LADEE missions involving amateur astronomers and citizen science in actually making observations that contribute to the science of the mission. For instance, on the LADEE mission, we had a number of amateur astronomers observing the moon during the course of the LADEE mission. As LADEE is flying around studying the atmosphere of the moon, we were looking at meteoroid impacts on the surface of the moon, seeing how those meteoroid impacts would correlate to changes in the structure and composition of the lunar atmosphere. We're working on opportunities for amateur astronomers to actually be measuring the orbits, measuring the positions and changes in the orbits of these near-Earth asteroids. That's very important because they don't feel constrained to be limited just by Kepler's laws of motion. And that makes them tricky. We're working with the SETI Institute just down the road here in a program where people have very simple security cameras pointed up at the sky. They're allowing them to record meteors as they come in. And if you get enough people from slightly different sites recording that meteor, not only do you see its three-dimensional path coming down through the atmosphere, you can calculate what its orbit was before it encountered the Earth. And that way we're discovering new meteor streams from comets as yet undiscovered, but whose orbits intersect those of the Earth. And we're working with the NASA Tournament Lab and Topcoder program to develop improved algorithms for integration of data from spacecraft, recently we've been working with LRO. We're looking at some other options, but integration of that data into our lunar mapping and modeling portal, which is now branching out into other planetary bodies too. Let's go to the next slide. A fun event that we have that I would like to invite you to is the International Observe the Moon Night. We've been doing this every year for a number of years now. We get people showing up at locations around the world. Here you can see Google Maps is actually showing us right now where people are signing up to have events. Our event this year is going to be on September 19th, 2015, and people will gather at these locations all around the world. We will be streaming out talks to these locations, and people gather with local amateur astronomers to see the moon. It's really, really an exciting thing to do. We have a lot of classroom visits, workshops, public lectures. A lot of these are streamed out to remote locations around the world. We've been working with Navajo Technical University on a number of projects. They're doing some really neat work in 3D printing. Exploration Uplink, Yvonne talked about our robot rovers out in our lunar simulant test bed. And also in our simulant test bed, we're going to be working this spring with some students who are working with the Swamp Works at KSC, Kennedy Space Center, on a payload, a proposed payload for the Google Lunar X Prize mission. So they'll be actually doing some testing in our simulant test bed there.
All right. So the other thing we'd like to invite you to is the NASA Exploration Science Forum. This is something we host every summer, and it is in person as well as virtual. But since you're right down the street, please just hop on over. We would like you to register, but it's free of charge, and it happens in July, the 21st to the 23rd this year. And it will be 3 days of listening to and interacting with people who are doing cutting-edge science and looking at how that science informs exploration. So please come to that. We have hosted a number of virtual events over the last several years. I mean, since the NASA Lunar Science Institute was formed, we've probably done more than 1,000 virtual events. And so you can always go to our website and see what's coming up, what's new. We have workshops, we have seminars, we have various things that might attract you and have some interest. So go to servi.nasa.gov, and if you misspell SSERVI, we tried to capture as many of those domain names as possible with the misspellings. Just try to remember SSERVI, it sounds like the disease. Okay. All right, partnerships in Silicon Valley. We're very fortunate to be here in Silicon Valley, and so we try to learn as much as we can from those of you out there doing this cutting-edge, wonderful new development. And so we have a picture there. What's being shown is a little robot that we have from the Double Robotics company. And we have a couple of those, and we use them for people to attend our forum when they can't be there in person, or just to come down the hall and have a conversation with us when they're not physically in the building. We also do a lot with next generation support, that is training the next generation. Brad Bailey, who's here in the audience, has done a great deal of this for the graduates and undergraduates that we work with. We've probably trained about 200 graduates who are now employed in academic and other positions. And by we, I don't mean the central office only, I mean throughout all of the teams that we've had as well. We've established new programs and promoted new faculty positions at various universities, and established things like Lunar GradCon, which is a conference that is run by the graduate students themselves, but we support them and give them the encouragement to do that so that they can get used to giving talks in front of their peers and get feedback and that sort of thing. There have been student exchange programs, NASA postdoctoral program where we try to put in bed a postdoc with two teams, at least two teams, so that they can benefit both teams and be part of that glue. Students are that unique glue that hold teams together in a way that I just love. And I see them grow up in one team, graduate, and go to another one, and then become a postdoc somewhere else. It's fantastic. So, okay, I think you can read the rest of that. Let's just go on. What's our future look like? Well, we've got the Exploration Science Forum, as I mentioned, in July at Ames. And the European Lunar Symposium that we also help, and that is in Rome, Italy, Frascati, which is in May of 2015, so we're looking forward to that. We have our next cooperative agreement notice. This is the vehicle by which new teams will apply to become part of SSERVI. I told you that the current teams are funded for 5 years. Well, every 2.5 years, we'll put out a new CAN, cooperative agreement notice, for teams to apply to. And that way, we hope to select the new teams before the old teams have finished their first 5-year stint. That will give us cultural continuity, and the older teams and the new teams will work together better. We have the potential for new international partners. We always hold special sessions at major meetings like the American Geophysical Union. This past December, we had an all-day session devoted to science and exploration topics. And we hope to continue the significant inter-team collaborations. In the first year of operation, these teams have already published over 195 papers and probably 400 conference papers. And this is just unbelievable. I mean, anyone who's gone through the peer review process knows it takes about a year to get something out from start to finish. And these teams have already managed to get 195 papers through that peer review process. So we're very proud of them, and we look forward to what they're going to do in the future. One thing that we thought you guys might like to hear about, lessons learned from our experience with virtual collaborations. I haven't talked to you very much about what we use or how we do it. I've got those slides if you want to know more. But we use Adobe Connect, and we found that that serves our purposes best. There are many ways that we could do this, but that is one that works for us. And so what we've learned over the years is that it's really important to conduct personal one-on-one training before we have anybody present. It's important to provide a checklist so that even though they think they're familiar with how to turn on their camera and set things up, they've got a little checklist they can go down. That saves a lot of time and trouble. Test, configure, and optimize the off-site video teleconferencing system. This is critical. We provide a technical producer and a host MC speaker who's familiar with what virtual communications are like. And that means that when there's some awkward pause or some time or something isn't sounding quite right, that MC knows the right thing to say, the way to keep everybody engaged, and the way to get us through the problem. We like to have redundant systems and backup roles so that there isn't a single point failure. That's something we've learned from NASA and the Apollo program. What experience has taught us? Create an environment that's inviting and has a real natural feel. Designate a facilitator for each event. Use social media and dedicated online discussion to involve and engage the online audience and the participants, as well as the speaker. And that's why we like Adobe Connect, because you've got that little chat box, that window where people can type in their questions. And sometimes you see people answering each other's questions in the chat box while the speaker just continues on with their presentation. Now, as a speaker, I find that really disconcerting. I don't like looking at that chat box. If somebody's asking me a question, I want to be the one answering it, not having somebody else. But it turns out a lot of other people feel differently. They love having that chat box, and so they really use it, and they go to town with it. And I have to admit, it's value added. And let's see, just try to accommodate time zones, that's obvious. 90-minute sessions work best. We try and follow those with a 10-minute break and have no more than 3 sessions a day or you're going to lose your audience. And in conclusion, I think the main takeaways for what we've learned from the Virtual Institute model is that by having longer periods of funding, the 5-year funding, that's long for scientists because usually they have to write proposals for 1 or 2, maybe 3 years. And by giving them a larger amount of funding, the teams each get roughly $1.2 million a year, and this enables them to then support their students. You can support a student for 5 years and get them all the way through graduate school if they start at the right time. But by doing this, we get unexpected discoveries from the interdisciplinary and inter-team collaboration that comes about through this research. So the whole really is more than the sum of the parts. And we see incredible productivity from these teams, so we know that the taxpayer, all of you, all of us, are getting a lot of bang for your buck. The ability to assemble the best possible team, regardless of where they're geographically located, and the cost savings that you get, obviously, by not having to travel everywhere, both in time and energy, really, I think, gets that productivity up. And the long-term stability for the students, our future workforce. This is so important to all of us. So with that, I think that's everything I brought, and I'm happy to answer any questions. And we've got, of course, Brian Day and Brad Bailey here as well that are also happy to take your questions.
Is NASA the first organization to try this virtual institute? I thought it would have been very popular by now.
Well, that's a good question. The National Science Foundation actually has tried this as well. I think their model is slightly different from ours, but I do believe NASA was the first. And I think with the NASA Astrobiology Institute, they have the longest running history from 1998 to now, and they are going strong. So we took a lot of our cues from what the NAI did, and I think the NSF probably learned a bit from what NASA did as well. But I don't know of other organizations. I can tell you that both the Office of Management and Budget and the White House have been interested in what we're doing, and just about a month or two ago they asked me to give them a presentation as well, because they're looking at how this might apply to other government agencies. So you might be seeing more virtual institutes in the future.
So what's the typical collaboration schedule for many of these collaborations? Do they all get together weekly or monthly, or is it just the PIs, or is it the whole ecosystem? That's
a great question. And the teams, so the question, it could be answered differently for the different teams, that they are allowed to set their own schedule and do what works best for them. But I know of some teams that have, almost all teams have at least a monthly meeting in addition to the monthly meeting that they have with us as a central office. All the PIs get together and report on what their teams have been doing once a month. But within their team, they do at least once a month, some of them on a weekly basis. And I think it really depends on whether their people are all co-located in one place or whether they're spread out and they need to tag up with them around there. But one of the things that we think is very important in running the Virtual Institute is not to over-constrain what the teams do. As a scientist myself, I know that I really appreciate the leadership getting the obstacles out of the way and letting me get my job done. And that's what we're trying to do with the teams as well. So when they have new directions, new ideas that they want to go down, they don't have to check in with us every minute of every day. If it's a major redirect, we'd like them to talk to us about it first. But in general, if all they do is what they wrote in their proposal, we would be disappointed, because we know that new science and new creativity and new ideas come at the intersection of many disciplines and those clever ideas that they get by having these weekly or monthly discussions, however often they want to do it.
So, I know a lot of other NASA groups still insist on face-to-face meetings. Many of the, Cassini, things like that, all their groups meet together. Do you think you could give advice to them as to whether such everybody needs to get together in the same room is still necessary, or do you think those face-to-face meetings still have a place, or do you think this is the future?
Sure, a very important message. I'm so glad you asked that question, because a very important message to take away here also is that virtual is not always the answer. And there are some really important reasons and situations where you want to have that face-to-face. And I know from the team activities, my husband, who's also a planetary scientist, has been on several teams, and I've watched what they have to do and the way that they have to interact. And right now, as they're getting ready for the Pluto encounter that's going to happen in July 15th, they're meeting on a regular basis in person every month or every 3 to 4 weeks, maybe even more frequent. Yeah, so, okay, you're part of that, maybe. Okay, and so that's critical. That's critical, and we are not by any means suggesting that this replace those critical times. But there are plenty of other times where we find that virtual does work great, and people ought to be open-minded to it and give it a chance. Also, I think the problem is that when they think virtual, they might think of some bad experience they had, where the audio was poor, the video was poor, you wasted a lot of time trying to get people set up. That is not what we do. Come and watch one of our video archived sessions, or join us for something, and you'll see the difference. And part of that difference is because we have a technical staff in the central office that provides the bridging among whatever platform you choose to join in by, or the practicing with the presenters ahead of time. You know, they try to debug it so that to the audience it really looks flawless, and the audio quality is high and the video quality is high, and your experience is much better. Your frustration level goes way down. So there are some cases where it works exceedingly well, and other places where I wouldn't try to replace the old-fashioned way.
All right, well, thank you very much, Yvonne.
Thank you. It's a pleasure to be here.